Much of this lecture is really best done in ChemDraw to show you better what the structures are supposed to look like rather than holding up a model kit and showing it to you. But broadly speaking, I also am interested in teaching you how to draw these things well. So that's why we're going to do a little bit of both. The main idea here is that in organic chemistry, six-membered rings are ubiquitous. They show up absolutely everywhere. Cyclohexane rings are something that you just simply need to draw and think about and study. However, when we look down on the ring itself and we view it two-dimensionally, we're missing a huge piece of how the ring is actually arrayed. In fact, when you hold up the model kit and look at it closely, what you see instead is that it doesn't look at all like the nice hexagon that you might think when you're looking down on it, but instead is a whole bunch of different staggered conformations. We'll talk about this a little bit more when we do conformational analysis, but the point is that this isn't a simple flat ring. Instead, it looks rather more like a chair, a lawn chair. If you're imagining where my thumb is as the headrest and the footrest down on the other end, this is what people refer to as a chair. There's another conformation that six-membered rings adopt, and that is a boat, where you can imagine someone sitting in this boat and I'm holding, say, the stern end of a canoe or something. This is also a boat-like conformation, just viewed from the side. It, to me, looks more like a house. Anyway, you need to learn how to draw these things. First and foremost, what I want to do is draw what the chair looks like. And the real message here is that chairs are drawn as a sequence of parallel lines. I always draw two lines first, angled over fairly steeply, parallel to each other, and then I draw two more lines that are going to be parallel to each other, and then two more lines that are parallel to each other. And that right there is the chair. The specific chair that I'm trying to indicate, you can now see, looks something like that. So the question then becomes, when you're drawing these chairs, where are the hydrogens coming off? And really what I want you to notice from this distance is that we have hydrogens that stick straight up and straight down vertically. There's a group of hydrogens that we will call the axial hydrogens, and where they are is vertically up and vertically down. And notice as well that when we're drawing this chair that we have parallel lines. So all of these hydrogens, the six hydrogens that I just drew that are axial, they're vertically up and vertically down. They're parallel to each other. But then when I go to draw the hydrogens that are actually in the plane, then what we have is these are going to be parallel as well to other hydrogens that are present. So this bond is going to be parallel to that one. Likewise, this bond that I'm drawing here is going to be parallel to this one, and so on and so forth. These are the locations of all of the easy to draw equatorial hydrogens. Then, to draw these two equatorial hydrogens, we need to be parallel to these two lines. So said another way, this is where that hydrogen will be, this is where the other hydrogen will be. And what we're trying to indicate here is essentially 109-degree bond angles for everything, and this structure should now closely resemble the chair that I've been holding for you. Again, notice the vertical axial hydrogens, and that all of the hydrogens that are equatorial are in the plane and parallel to the rest of the chair. Properly, of course, I should have drawn those as hydrogens originally. The drawing on the board did not contain hydrogens initially because I wanted it to more closely map the model kit that I'm holding out. But to be fully correct, the chair, when drawn out, has to have hydrogens found at all of these positions. Otherwise, what I'm indicating is a whole bunch of methyl groups. The other thing I would like to do now is draw the other version of the chair. So a chair can be in this way, or I can also flip the chair over, and what I end up with is precisely the opposite of what I started with. Said another way, what I can do is take this vertex right here, bend it down, take this vertex and bend it up, and now I have the opposite chair of what I started. Again, if you hold these four constant, bend up the one vertex, bend down the other vertex, this is what we call a chair flip. So you should be able to draw the chairs in the opposite cases. So what I'm going to do now is leave those equatorial hydrogens in red, except now that we've done the chair flip, they all end up vertically, and they will be the axial hydrogens. So let me quickly draw those in. And then the black hydrogens that were originally axial now become equatorial. And again, when you're drawing these equatorial hydrogens, you have to try to ensure that you're drawing hydrogens parallel to the bonds that are already present in the chair. And again, it's these parallel bonds that we're going to mimic when we draw the hydrogen that comes out towards you and goes back away. As you can see, for whatever reason, I'm much more comfortable drawing my chairs this way, and I have a much harder time drawing the chair flip. You will almost certainly find that to be the case as well. In the upper right hand corner of the board, I am showing you the boat the way I've chosen to draw it, and I've kind of exaggerated the flagpole hydrogens, which is to say these two hydrogens up here pointing toward each other. The other thing I'm trying to point out with what I've drawn is that the four hydrogens on the bottom are in fact almost vertical. You could set this down on a table and this boat would sit quite nicely. There are four more hydrogens I should really draw for this to be complete. I find it's really hard to draw in the four blue hydrogens that I've now drawn in. I don't necessarily find it easy to draw those, but again, we tend to focus more on the chair representations of cyclohexanes and less on the boats. Finally, in the bottom right corner of the board, I have drawn for you a 2,2,1 bicycloheptane structure, and this is what it looks like. It's essentially a boat, six-membered ring, with a bridgehead carbon sitting on top of it. So this is a boat where you take the two flagpole hydrogens and put a carbon on it. So that's what I'm doing there. Now I'm going to draw for you where all these extra hydrogens are. And again, I've tried to indicate for you where the hydrogens are in the 2,2,1 bicycloheptane type structure on the bottom right. The main point is that we tend to look at this structure of cyclohexane and think of it as a two-dimensional molecule, but in fact we should always be thinking about the three-dimensional structures. The most important structure for a cyclohexane is going to be the two chair forms. Here's one. I can do a ring flip and access the other chair form, and really these are the two things that you need to be aware of. For this, what I really wanted to show you is the framework for the chair in ChemDraw version. So I was drawing this on the board, but this is the carbon framework for a chair, and this is the carbon framework for the flipped chair. In ChemDraw, I'm also showing you now the red equatorial hydrogens. So all the hydrogens that are in the equator, that are in the same plane as the ring, are now drawn in red in this particular chair form, whereas the axial hydrogens, the ones that are vertically up and down, are in blue. When you do a chair flip, what you do is take all of the red equatorial hydrogens, and now they're going to be red but axial. Everything that was in the plane of this chair is now vertically above or below the plane of this chair, and vice versa. The blue hydrogens were axial, they were vertically up and down, and now they are in the plane. That's what happens when you do a chair flip. In addition, I'd like to show you this in Chem 3D, again showing you that our model kit is a pretty good representation. What you see here is the lawn chair that I was describing. Here's the headrest for someone lying in the lawn chair, and here's the footrest. Your mileage may vary as to whether that is actually a good representation, if a chair is a good name for it. But the other thing I want to highlight is how everything is parallel. There's parallel lines absolutely everywhere, especially clear with the vertical axial hydrogens. And the equatorial hydrogens, likewise. This bond between carbon and hydrogen is parallel to this bond between carbon and carbon. This bond between carbon and hydrogen, also parallel to this bond right there. Unfortunately, it is not possible to force Chem 3D, at least as far as I know, to show you the boat conformation of a chair. So I'm going to simulate that by showing you instead the bicyclo system we talked about earlier. Here, you're going to have to imagine that this carbon on top is missing, but then the boat is made right here, and these would be two flagpole hydrogens pushing toward each other. Unfortunately, when I go to delete this carbon, what it does then is find the lowest energy conformation of a six-membered ring, which of course is a chair form. Anyway, this is a couple of different views of a boat, or specifically 2,2,1 bicycloheptane is what you're looking at. But if you remove this carbon, the shape that remains below, that would be a boat. When you learn how to draw these molecules, really what I would like you to do is to practice by holding the actual model kit in front of you as you're trying to draw. Make sure that what you're drawing resembles the model kit that you're holding in your hands. If you work on it, I promise this will be easier to spot over time. But really the advice is find the parallel lines when you're drawing chairs, and there are parallel lines in boat frameworks as well. Shortly, when we analyze cyclohexane conformations, we'll be interested in trying to decide how much energy it costs to have a methyl group be in one position versus the other. But for now, I'm interested in you learning how to draw these well. And I'm also interested in you starting to realize what happens when we do a chair flip. Namely, right now, this methyl is axial and is vertical. But if I do a chair flip, flip this up, flip this down, then now I'm in a different chair conformation, and now this methyl is equatorial. Presumably, it's better for the methyl to be in one position or the other. We'll talk about that at some length and why in future lectures. For now, though, it's really a matter of learning how to draw this picture well, and doing so while we're contemplating other stereochemical considerations is really the right time to learn how to see the difference between the axial and equatorial hydrogens, and to start trying to draw them as a series of parallel lines.